problem, one example. The federal government is planning to establish storm shelters and emergency response facilities in the south of Florida. The government wants to build a minimum number of stations to ensure that at least one station is near 1 hour drive from each city. Basically, in whatever city you are, there is a shelter in a 1 hour or less distance from you. The time, it could be expressed in miles too. The times in minutes required to drive between cities are given in this table. Formulate an LP that provides the minimum number of facilities within 1 hour drive from each city. All right, no problem. So, again, think about what is the first thing the data is given to you, that's in this table. But we learned that each optimization problem has a decision variable, set of decision variables, and so forth. Decision variable includes the solution. So if you were to give a solution for this problem, a hypothetical, a random solution, what would it be? What is the problem asking for? What is the formula, the LP that provides the minimum number of facilities? So what is a trivial? What's a random answer you would give for this solution? For this problem?
Facilities.
5 facilities. 5 facilities. We have 5 cities. Just buy 1 in each, right? So the answer is 5, but you also need to indicate where those 5s are, which is in this case 1 in each city. Another answer is 2 facilities, 1 in 1, 1 in city 1, 1 in city 4. Another solution is 2 facilities, 1 in city 3, 1 in city 5. These are all different possible answers. So basically, if I have 5 cities, build 1 here, 1 here, 1 here, 1 here, 1 here. That was your first answer. Then I gave another answer saying that build 1 here, 1 here. Another answer would be 1 in 3, 1 in 5. There's so many different ways I can give you an answer for this problem. Here the objective function value is 5. It's asking you what is the minimum number. So the number of facilities you make is is the objective function value. Objective function value in the first one is 5. Value of z equals 5. The second one and the third one is 2. Okay, but so how can what do you think would be a good choice for decision variable in this case? I kind of gave you a clue. I'm having a cell for each city, 1 through 5, and then if it is 1, I'm gonna build facilities there. If it's 0, I will not do that. So what do you think is the decision variable? x1, x2, x3, x4, x5, right? xi equals 1 if I build a facility in city I, and it's 0 if otherwise build a shelter. So I got the xi, 1 if shelter is built in city I, and 0 otherwise. So if that's the case, what is the objective function value? Objective function formula.
Minimum of x1 plus x2 plus x3 plus x4 plus x5.
Yep. So minimize z equals x1 plus x2 x plus so forth, which I can rewrite as summation of xi's, I goes from 1 to 5. And again, now trying to add the constraints. What will be the constraints? If I ask the computer to solve this, what would be the first answer? Would be 0, 0, 0, 0, because that makes z, sorry, minus infinity for each one of those. But I'll add this constraint down here that ensures your x1 through x5, those are either 0 or 1. And then the computer says, okay, fine. Make all of them 0, your objective function becomes 0, and there is nothing less than that. But we know that's not a good solution because we have a constraint here that says the government wants to build a minimum number of stations to ensure that at least one station is near 1 hour drive from each city. How do I formulate that? How do I ensure that there is a 60 minutes or less shelter from each city? For example, this solution, 1, 0, 1. So build 1 in city 1. Build 1 in city 3. If that's the case, city 1 already has 1 close to it, which is itself, it's 0 minutes. City 2 has 1 close to it, which is 50 minutes. It's less than 60 minutes. Also, it has 3, which is 45 minutes away. City 3 also has that one. City 4 has 30 minutes, 30 minutes. Why? Check. City 5 also has 20 and 45. All right, so that's a good feasible answer. But how do I get to that point where that one is enforced? Or this one, if this is the solution, only build one that has a station only in city 1, objective function will be 1. 1 has 1 close to it, 2 has 1 close to it, 3 doesn't have anything that's under 60 minutes. So this is not a feasible solution. Not good. This is feasible, but very expensive. So what do you think our constraint, what is a good approach in writing the constraint? The answer is in the problem, in the question. The city wants to ensure that at least one station is near each city. How do I write that? Make sure there is a close by shelter near city one. How do I write that as a constraint? Just look at these. Which one of these are qualified for city
Turn
one?
that into a binary matrix where like anything that's less than 60 is 1 and anything that is more than 60 is a 0.
Perfect. Perfect. And then you multiply those by the and then what? So yes, first thing, I'm gonna turn this table to a binary table where 1 means it is close enough, 0 means it's not close enough. So good suggestion. 1, 2, 3, 5, 1, 2, 3, 5. And no style. So these basically the only use of these numbers here is whether they are close enough, right? Otherwise, we don't really care what is the actual distance. For example, 0 is close enough, 50 is close enough, 70 no, 30 yes, 20 yes, and then 1, 1, 1, 0, 1, and then 0, 1, 0. One, 0. Basically, if it's under 60, I make it a 1. If it's more than that, a 0. All right. And then we had another matrix that would say, if I multiply this by the matrix of variables, which are all 0, 1, so this would be x, 1, 1, or sorry, the vector of variables. What would I get? Make sure that how can I utilize this matrix now to write my constraints? For
So
city.
you, sorry. You can, yeah, like when you multiply the vector by the matrix, you just make sure that the sum of the elements in a row is greater than or equal to 1 for every row.
Yes, great, which means at least one of these ones is selected, right? Basically, I have x1, x2, x3, x4, five variables here. If you multiply each row by these variables and make sure that the sum is less than or equal, greater or equal to 1, that gives you the constraint, which means for city 1, make sure that x1, 1 times x1, 1 times x2, 0 times x3 doesn't appear here, plus 1 times x4 and 5 less than greater than or equal to 1, which means that at least one of those need to be 1. If that's the case, you will have enough shelters close by. Same thing for city 2, city 3, and so forth. For city 2, which one of these are close enough? x1, x2, x3, x5, x1, x2, x3, x5. For city 4, x1, 2, 3, and 4, 5. 1, 2, 3, and 5. These have to be greater than or equal to 1. All right, so 5 constraints here, 1 for each city. Is that a good solution? And I'm going to write all of these in a more condensed way, more mathematical way, which is this. Make sure sum of xi's is greater than or equal to 1 for each city, j, 1, 2, 3, and this I needs to belong to the set Sj. So each city has a set of cities that are close to it. For example, this is for city 1, this Sj is what? 1, 2, 4, 5. For city 2, S2 is 1, 2, 3, 5. For city 3, Sj or S3 is 2, 3, 4, 5, and so forth. So this is a mathematical way of saying the same thing for all these 5 constraints. So I can rewrite the set covering problem by saying that I'm gonna make it as small as possible. This is the set covering problem. And here I can say J in C, which is the set of all cities. And here I can say I J, sorry. So here it's basically a practice. I'm trying to say J in, again, set C, this is XJ, here again. One, if city, if node xj equals 1, if node j is selected and 0 otherwise, then j again is in that. So now this we would say this is a generalized or generic formula for set covering. It's not for a specific problem such as finding the shelters. It applies to any problem in which you have a set of nodes and you want to select a bunch of them, that covers some other nodes. For example, let's say this is actually a project that our students are doing. They are making bikes. Sorry, they are solving a problem for the master project is finding where to put charging stations for scooters on campus. So you have what they did, they basically created a grid on the campus, Cal Poly Pomona map. They made a grid, and then each point in that grid was one node. And then the walking distance between those nodes, you would know those. And based on that, they decided where to put the charging stations so that from anywhere on campus, from where the lectures are, students can walk to a close by charging station. That's also a set covering problem. And the model for that is the same thing that you see here. Yeah. And then SJ needs a definition here. I'm gonna add it here. So this would be a very general for set of all cities covered by the node J. All nodes, sorry, not cities. So this is a generic format for set covering problem.